Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a great pleasure to welcome Emery Burger, who's visiting Microsoft for a month, and he'll be here, so if you're interested in talking to him, there's plenty of opportunities. Emery is a professor at the University of Massachusetts, where he's been since 2002. Emery got his PhD at University of Texas in Austin. His research has investigated various aspects of systems, including operating systems, performance, memory management, and he's published numerous interesting creative articles, some of which he's going to talk about today. He's also known for delivering systems and having, for example, the Horde memory allocator, which is widely used for parallel memory allocation. So it's a great pleasure to introduce Emery. He's going to be talking about multiprocessors and how to use them.
All right. Thanks, Ben. Right, so the title of my talk is Exploiting Multicore CPUs Now. So here's the issue, right? So for years and years and years, ever since I was a baby, people were saying, one day, dear God, there will be parallel computers on everybody's desk, and we all laughed. And we thought the professor was crazy, and then they kept saying it over and over and over again. And then we started thinking, oh, maybe it'll be true. And I remember in like 1992 thinking it was just around the corner. I guess 14 years is just around the corner. So it is here. Finally, we have these multi-cores, right? So this is great, except now we don't really know what to do with them. So we thought what we were going to do back in the 80s and 90s was we would all be using parallel programming languages. And that apparently has not panned out. So it seems that the current idea is let's rewrite all of our software from scratch. But this has numerous disadvantages. So multithreading has lots of issues that are well known. You have to deal with race conditions, deadlock. In addition, you can't just multi-thread your code and say, yay, it works, right? In fact, just giving a thread to every task doesn't scale at all. So it's actually quite a bit more complicated than this. You have to deal with scalability bottlenecks, and you really have to get into your code and understand it quite a bit. So there's been a lot of research recently on addressing one or two of these problems, which is this notion of atomicity, right? So replacing locks with atomicity or transactions. And this is a good idea. It's a very popular direction. It doesn't really solve all the problems. It addresses some of them. I put functional programming up here in question marks. The functional programming people are excited again because they said, look, this Kool-Aid that we've been drinking and we've been trying to give you, you should really have some now. Again, it's still under the rubric of rewrite everything, right? So I have to take all the code that's been written, there's a few hundred lines or so out there that need to be changed, and then rewrite them, right? So problem solved. The other alternative, of course, is parallelizing compilers. And I actually saw a keynote, and I will not quote the person, where the person said, now that we have multiple cores, we're going to get serious, and we'll really have parallelizing compilers. And I thought, oh, that's what it was. We were all frivolous before for 40 years. We were just fooling around. Maybe somebody will have some great insight. But I think it remains a very difficult problem. Right. So this talk is about two different approaches that actually allow you to take advantage of multi-cores today without rewriting any code. So the idea here is we're going to take legacy applications and somehow do something with them that lets us either make them run faster, that is, take advantage of all of these cores, or increase reliability. So the first thing is a language for building servers called Flux, and the second thing is a system called DieHard that is meant to increase reliability. So I'm going to talk about both of these in turn, and first I'm going to talk about Flux.
I thought you were saying no new code, and now you're giving us a new language.
So that's a good question. So let's say we'll get there.
The story's in Flux.
Yeah, there you go. It's you'll see. It's not much new code. All right. So here's the motivating example. So I'm going to use this as a running example through this talk. The idea here is we're going to build a server. So we want to build a server, and here's this very straightforward idea of a server. I'm going to have a server and a client, and the server is going to give up images, all right? And it's going to store them in raw format. So it can make them any arbitrary resolution. But the client only wants a particular resolution, and here we'll use this URL-like approach, right? You go and you want the Easter Bunny 200 by 100 size, 75 DPI, right? So the image server can go ahead and dish up this image. First, probably it's going to look in a cache to see if it's given it up recently, right? Around Easter Sunday, this might be a good idea for this particular image, right? But if it doesn't find it, it'll go and get it, shrink it to the appropriate size, and there's your Easter Bunny, okay? So this is a pretty simple server. The problem is, if you go ahead and you write this in the obvious sequential fashion, it doesn't scale at all, right? So you could write a loop that goes and waits for a client and sits in the client, it does all the processing and gives it back. This is not going to scale up as you add clients. In addition, if you have 1,000 clients, right, you're going to wait for 999 people in front of you. So this is a latency problem. In addition, if you have multiple cores or even multiple processors, you're not going to take advantage of it, right? So this is well known. So one thing we could do is to use threads. So we could, for instance, be naive and have one thread per client connection. This has numerous problems. I guess I don't need to go into these. One of the serious problems is it mixes programming logic with concurrency control. It's not so clear this is a big problem if you do a thread per connection, but a thread per connection doesn't work. You actually have to have much more complicated software architectures to get any reasonable scalability and performance. And by the time you're done, your server, this very simple, little, elegant, tiny piece of server code that you had, is embedded in a gigantic framework. And you have no idea what's going on. Yeah?
Can you say just briefly what you mean by limit reuse here?
Right. So, so threads limit reuse. So, let's see. What the hell did I mean by that point? So there's a number of different issues. So if you are going to use multi-threaded software architectures, then you have to worry about the synchronization primitives, right? And you may have to change libraries. You may have to do all these things to work in a particular framework. So for instance, you can't just straightforwardly say, we're in Windows land, right? There's apartments, and there's threads, and there's processes. Pick one. Well, now you're stuck with that one. So that's what I mean by, that's what I think I meant by limiting reuse.
Does it go with the mixing and the concurrency control, or maybe the library is built for a certain concurrency model?
That's right. Yeah, the libraries. So threads, basically, once you say this is going to be threaded, now you're stuck with threads. If you wanted to say, oh, I meant to be event-driven, right, well, that's not going to work. Yeah, exactly. Okay? It's sort of baked in. Right. Okay, so this first half of the talk is about this programming language called Flux. It's a lightweight language. Basically, you can think of it, in a sense, as a high-concurrency glue. And the glue is going to combine components. You're going to direct them into a flow, which corresponds to the flow through the server. And then you'll add some atomicity constraints. So the components are going to be unmodified C or C++ code. I have or Java kind of grade out there. We do have a Java system, but the focus of this talk is on C and C++. The flows are going to be these implicitly parallel paths through these components. And I'll explain and show examples of how this is going to work. And then the atomicity constraints are a very high-level way of expressing mutual exclusion. So you give Flux the Flux code, you give it to the compiler, and you give it the components. And the compiler will generate a number of things. So the first thing it can generate is it'll generate a server, right? So the server will have certain properties. It's going to be deadlock-free. Notably, it's runtime independent. So you can generate multiple styles of servers just with compiler switches and a different runtime. So for instance, you could have threads, the naive model, you could have thread pools, you could have events, and more. You can actually just keep adding runtimes. It also supports ball and lattice path profiling automatically. I'm not going to go into this any further. That's the last mention of that. But something that's very nice for performance prediction modeling, it also will generate a discrete event simulator for you that you can later use to actually predict the performance of your system as you add resources and clients and measured under load and so on. And I'll show some results from that later. So first I'm going to talk about Flux. I'm going to go through this exercise of building up a server from pieces and talk about these various aspects of the language. I'll present some performance results and talk about some future work. All right. So we need to start the program with main. So the main in Flux is a source node. So a source node here is basically intended to initiate the connection. So the source of all of the stuff that's going to happen is going to be a connection from somebody. You're going to listen to something. See if the laser works. And I can't see it at all. It's a disadvantage of color blindness. Or, yeah, it works. All right, anyway. So the source here has this thing listen, say, accepts a socket connection, and then it sends all of its data down to image, which is some node that's going to produce an image for us. Okay? The thing to understand about source is that source is conceptually executing inside any of these sources in a separate thread and running forever. So a source node is just constantly here, waiting for a connection, processing it, and going on to the next connection. All right? Okay, so now we want to build up an image server. So an image server here is going to require a few pieces. We need something that's going to manage HTTP parsing. We need something to manage these connections and sending stuff out over sockets. And then, of course, we need something to compress these images into JPEGs. So we can actually go and get most of this stuff just out on the web. There's sequential C code to do these things. In particular, there's this live JPEG, which is very convenient, which does exactly what we want. So what we're going to do is we're actually going to define, so image, this whole thing, we're going to decompose into pieces. And we're going to implement these pieces by making calls to these various libraries. So here, this abstract node image is going to be represented by a bunch of other nodes in this flow. And these nodes can themselves be abstract nodes, which you can think of as just yet another flow, or they can be concrete nodes, which actually mean they directly implement some piece and call these things. Now, I should add here, you do need to add a type signature to these so that Flux will know, well, whatever's coming out of read request is actually legitimate to go into compress. Yes?
This is probably jumping ahead, but since this is the point at which you introduced the idea that these nodes can be implemented with sort of concrete legacy sequential code.
Yes.
I'll ask it.
Go ahead.
Does the system offer some way, which seems like the first question to ask, to get concurrency at a finer than component granularity? Because it seems like that the big challenge to get over, right, is that if each of these components is written as sequential code, you have no way from the outside of reasoning about how you might be able to run it reentrantly or concurrently correctly.
Right. Okay. So there are two issues. So the first issue is extracting more concurrency, and the second issue is safety for legacy code. Right. So I'm really glad you asked these questions. So so the first one.
The answer can be we'll learn that.
No. The first one is actually really well motivated, and here's the deal. You know, if you have a client-server architecture, and you're going to be serving a bunch of clients, right? Are you going to be serving, let's say you have 4 cores. Are you going to serve 4 clients? You're probably going to serve more clients than you have cores. What that means is that the amount of parallelism you have is actually embarrassingly large if you consider it from the point of view of each client executing. So I actually don't care here about parallelism within each of these chunks. All I want is parallelism across all of the clients. So once I have parallelism across all the clients, then I need to protect some state. So suppose, this is not the case for most libraries, but pretend live JPEG is non-reentrant and deals with some global thing. Well, I need to make sure that only one thread at a time gets into live JPEG, if I'm actually using threads. Okay?
So it sounds like the answer is no. This system doesn't give you some magical way if live JPEG is not written reentrantly.
No matter.
Somehow magically get it to run concurrently.
That's correct. Sorry. Yeah, all of a sudden there's a bolt for the doors, right?
That's totally right. Because that's true, it seems like a lot of problems become to chop up your code into sort of correctly, independently executable chunks, which is an advance over the current state of the world, but is sort of roughly the same problem that you have today when you sit down to try to make a big lump of sequential code parallelizable, right? You have to reason about where there are appropriate seams in.
Yeah, I'm not entirely convinced of that, but I think the more interesting thing about it is to think of it as, I want to build functionality. Let's say I just modularize my functionality into sequential pieces, right? The code is entirely sequential. And somebody else is going to handle all the parallel glue and all that stuff for me. So all I really need to do is reason about my program as sort of the way I've been trained to do for the past N years. As sequential code, which is hard enough. Right. Okay? And in addition, this, software, the only, to my mind, really successful software component model out there has been libraries. And libraries are already well encapsulated and nice chunks of things that people have delivered and used over time. So it's an attractive way to build software, I think. Right. So I'm going to get to the stuff about how you protect the node execution. But the key insight here is that when it comes to parallelism, if I have 1,000 clients, 1,000-way parallelism is plenty. I don't need the parallelism within each flow. Okay. So control flow. So I mentioned caching before. Well, caching has a control flow, right? It says, is this a hit or is this not a hit? So what I want to be able to do is I want to be able to distinguish between these cases and have, in effect, two different flows. But what I don't want are variables. I don't want any programming language stuff here at all. I want it to be very high level and easy for the compiler to understand. And in fact, I don't need variables. What I do need is what I call a predicate type. So the idea of a predicate type is, here's this thing, test in cache. Test in cache is a black box. It just returns true or false. It's a Boolean function. The user supplies it. And I then can treat it as a type, and I can do this matching, which will look familiar to people who've used functional programming or Prolog. The idea is I'm going to check this node handler, and if the third argument, the value is a hit, that is, if I apply this Boolean function to the third argument and it returns true, then it will do nothing. If, on the other hand, it doesn't, then it will fall through to this case. This means don't care, don't care, don't care. And then it will go to this other flow. So visually, this is sort of what it looks like. It says check cache has a hit, handler does nothing. Otherwise, handler expands out to these other nodes that actually go and fetch the thing from the cache, add it to the cache, and then return. You had a question?
So do you expect that nested caches side effects?
Yes. That would be bad otherwise. Yeah. Tom?
This is just ringing bells. How is this related to what Jim Laris did with
Stage server.
There's stage
server?
Yeah.
There we go.
Yeah.
Thank you.
Mm-hmm. So stage server is really a runtime system.
Right.
It's not a language. That said, you could view stage server as a potential candidate runtime system for Flux. We haven't actually implemented stage server-like runtime system, but there's nothing preventing us from doing so, because we basically know what all of these. Oh, the arrows mysteriously disappeared from here. Yeah. By the way, PowerPoint. Is anybody here from the PowerPoint group? Yeah. If you all know somebody or know one other person, tell them when you copy and paste something from one presentation to another, like all the arrows mysteriously disappear. But then, let's see if this works. I'm not going to do it live. If you click on it and move it like a fraction of an inch, all the arrows suddenly rematerialize. Which is, yeah, so I forgot to do that. Anyway, yeah.
Is part of what you want to address in the language the synchronization of these events or tasks that you spawn off to different processes?
So, yes and no. I mean, that's just part of it. So let me talk briefly about stage server. For those of you who aren't familiar, stage server is this thing where basically the idea is as you're running a bunch of things in a server. So for instance, we go and we have read request. If you were to be able to take, say, 1,000 of these incoming connections and then execute the same code on all of them and then sort of advance them to the next stage all at once, you get a lot of iCache locality because you're executing the same code over and over and over again, and then you'd advance everybody forwards. And stage server works in this way. It sort of gets everybody to one stage, processes as many people as it can in that stage, and then moves them to the next stage. So it's a kind of a hybrid, event-driven, and with queuing and threads, and you can have multiple threads at the stages to dispatch and so on. It's somewhat similar to a system called SETA, which is another staged event-driven architecture. Really, I view these as being implementation details in effect. Right? You can, given this high-level structure, the compiler can generate any of the needed information to hook it up to that kind of runtime system. Whereas when Jim and Mike were building their stage server web server, which admittedly was also quite a piece of work, because lots of engineering went into it, but they also had to really adhere to this API. So they had to write all this code themselves and glue it all together, and so we would do that automatically. Okay. All right, so here's the control flow. So these are these predicate types. Fine, so now I have caching. Well, now we're back to this problem of atomicity. So I've got this cache. Well, I need to keep the cache consistent. So what does that mean? It means I need some sort of mutual exclusion. So the way I'm going to express this mutual exclusion is I'm going to express it in the language. I cannot, it's a design decision, I cannot put any flux into this code. The code is off the shelf. I don't get to go in and modify it and add locks to things. All right? So what does that mean? I need to put it in Flux. So what we do is we add these little sections. We say if you're in this node, check cache or complete or store in cache, then you have to own one of these locks. So you can think of them as locks. And basically it's a two-phase locking protocol. So you acquire all of them before entry and then you release them. So here these alphas mean all of these three things are exclusive. Now it may be the case that complete also cannot run with some other thing that has this atomicity constraint beta. And that's how you do this. So if you want multiple things to be prevented from running together, you just put the same symbol in these atomicity declarations. And it's worth noting that this doesn't just apply to a node. So here we have check cache and store in cache and complete. We could also make this whole handler atomic just by saying atomic handler and then giving it some label. Yeah?
Is this just sort of an arbitrarily constructed example, or might there be some real-world reason why check cache, store in cache, and complete in particular are...
Right. So complete actually here, so this is from, with the exception of the beta and the Greek letters, this is drawn from the actual example. So we have an image server example. And complete here, the way it works is we actually have some reference counts because the images themselves are maintained on the heap. So you can't just evict it and erase it from the cache until you know nobody is using it. So when you walk out of a connection, you then complete and decrement the ref count on the image you're holding. It's a good question. OK. So these atomicity constraints, was there another question? Yeah.
So each of these boxes can have sub-boxes, right? And they can have their own atomicity constraints.
They can, absolutely. OK. So this is fine, but it's pretty coarse-grained. So there are other things we might want to do. So we have some other relaxed atomicity constraints. In particular, we have reader-writer constraints. So by default, an atomicity constraint is a writer. Here we decorate it with the exclamation point. So it is a default. If you want to, you can also add a question mark. And then it'll generate reader-writer locks for you. In addition, we have these per-session constraints. And this takes a little bit of explanation. So suppose, this is motivated by BitTorrent, suppose you have some data. And the data needs to be updated on a per-session basis. That is, you've got some downloading that's going on. And you can have multiple connections from a user to a BitTorrent seed, downloading different pieces. And so BitTorrent just needs to keep track of how much you've downloaded, because it has this fairness protocol to try to prevent people from leeching bandwidth. Okay? So you're uploading stuff, you're downloading stuff, it has to update the state. But you're independent of everybody else in the world. Right? That state, however many bytes you've uploaded or downloaded, has nothing to do with however many bytes or downloads or uploads that Joe is doing. So what that means is that you really want this granularity to operate on a per session basis. So you add this word session, and then you have to supply a session function. And the session function takes output from the source and hashes it to some integer. And then basically you can think of this as being a hash table of locks. So this gives you fine-grained locking. OK? All right. So suppose you did two-phase locking, and you just acquired these things in the order given. Well, that would be bad, because you would quickly get deadlock. So here, if you have A and you have B, and A goes Z then Y, and B goes Y then Z, that's not good. So what do? So we sort them. So that's easy. Yay, no deadlock, problem solved. Well, not quite. So the problem is, this canonical lock ordering works fine, and you can sort all of the ones within the constraints. But when you have abstract nodes, this does not work, because you can have this nesting. So here's a case where you could have deadlock. So here A is really just an abstract node that holds B, and C holds D. Okay? So what happens here is that A, first you acquire Z, then you acquire Y, but then C is going Y then Z. So now you have deadlock again. So basically the problem is that you can't just sort these things independently. You have to realize that there's a hierarchy, and you need to somehow impose an order on them that applies all the way down the hierarchy. Right? So the algorithm we employ here is actually fairly straightforward. This is a little example. All right. What we do is we elevate these constraints. That is, we push them up in the hierarchy, and we sort them, and then we see if there's deadlock. And if there's still deadlock, we push things up again. And we iterate until we get to a fixed point. So here we have, but where before A just had Z as its atomicity constraint, now the atomicity constraint from B has been propagated up and then sorted. Yeah?
So what if the B is dependent on a predicate?
What if B is dependent? Oh, so, right. So B could be controlled by a predicate, right?
Yes.
It doesn't matter.
So basically you'll require it to take the logs for all of the subcomponents that may possibly be entering?
Yeah. So if you say that B is atomic with Y, that's what you as the programmer are saying, right? If you don't say that, then that's fine. I mean, the more serious concern here is that this obviously could lower the amount of concurrency available in your program. So the compiler actually, when it does this, it issues a warning. It says, I had to elevate these constraints to avoid deadlock. Maybe you want to do something different. Okay. So this is the last piece of the language. And this is actually something that took us a lot of head scratching to come up with. So what happens when you have an error? So suppose, for example, you go to load an image, right? You request Easter Bungie, all right? And it says, oh, there's no Easter Bungie, right? I need to do something else. Well, SETA, which is this alternate model, had this mechanism where you'd say, oh, there was an error like here. Now I need to send back a message to my predecessor. Then the predecessor needs to be able to deal with this error. And then this needs to be able to deal with this error, and so on. So it's like manual exception handling. And what this means is that every single component you write has to be prepared for any arbitrary error that could happen downstream, which seems to break modularity to me. Not only that, now you need to rewrite the code, or you need to write these crazy wrappers that somehow can deal with this. So what we do instead, we basically just have an alternate path. So we say if an error happens in read in from disk, we go out of the normal flow. And here we go to this 404, which just prints up the horrible 404 message. So I didn't say this was great error handling in this particular case, but you could imagine a message that says, right, the file you attempted to find is not available, right? And that would be fine. So the nice thing about this is that it doesn't muddy the normal flow of the program, and it allows you to have these custom error handlers wherever you want. You just have to have this one piece, and it goes right from the error that you wanted. Now, one extension that we've looked into, we haven't actually implemented it yet, because we have these paths that are coming with these numbers that uniquely identify every path through the code. We could actually have arbitrarily Baroque error handling. We could have a path, right? If you went here, then somewhere else, then here, then we could have an error handler for that. And then we would have to modify the language to allow something more complex on the left-hand side. We haven't yet seen a need for it. But it seems like a cute thing. Manuel.
So my question is about your box hierarchy. It seems like once you add these kind of arrows, the hierarchy is gone. I have to look at my thing as a flat list of atomic nodes, because otherwise your boxes, they have now funny output edges, right? It's no longer a sort of a nice box diagram.
Yeah, so we constrain the errors basically to be sinks. So when you have one of these error paths, it basically is going to be the end. It's a termination. So you could imagine having it be less constrained, but I think that way it makes it fairly simple to reason about. But I agree. I mean, ultimately, if you have any sort of error handling, if you don't do it in this sort of scoped way with exceptions, then you're breaking modularity in a way. But unfortunately, it's not clear what the alternative is. Okay. So this is the almost complete code for the image server. I say almost complete because I've omitted the type signatures of the concrete nodes, right? Which is not terribly interesting. So I argue that this is fairly short. It's not much new code. And it allows you to write this image server that actually scales and performs well and does all these things. Yes?
So what, instead of one cache, you had 4 caches.
Okay.
To look at if there's a hit in any one of them.
Yeah.
you don't let me count the number of hits.
Okay. Let's see. So there's not anything more powerful as a return value from a predicate type than a Boolean, but its input argument could be anything. So if you wanted to say, at least 7 for your predicate type, that would be fine. Just think of this thing here, this hit, which I left off the type def for. Think of that little function as being whatever you want that just comes from whatever this input argument is. Right? So this argument that comes into handler could be anything. Okay? All right. So good. So that's basically the overview of the language. Now I'm going to briefly present some performance results. So this wouldn't be terribly interesting if it performed like crap, right?
Are you going to talk more about how you compile this stuff? Or
I'm not. I'd probably be better to talk about that offline. Briefly, the compiler is all written in Java, and it generates C output. And
threading events.
Yep. And then so it depends on the particular runtime. There's a backend for every different runtime, and then the backend transforms things differently. So all right, I'll talk about this briefly. So if you want to you can do a naive thread model. The naive thread model goes from a source and produces one thread that executes all the way through to completion. The thread pool model is similar, except obviously it builds thread pools. And there's an event-driven system that basically turns this thing into an FSM and a giant switch statement and says, all right, I just finished stage 1, now I go to 2, right? If I'm here, then I have to do this check to decide whether I go to stage 7 or stage 12 and so on.
And where's the concurrency there?
In an event-driven system? So in an event-driven system, what you do is you basically you have threads that handle blocking system calls, but most of the computation is actually done by one main thread. Okay. Right. So right, but you get good latency for other reasons.
You don't actually have one backend that's like the stage server.
Not yet. No, we actually have another interesting backend. Well, I'm not so sure about that. The thing that we wanted to compete against, and I'll show you in a second, were these two systems, Capriccio and Seta. Capriccio is this fast user-level threading system that's a follow-on to Seta that actually uses, it looks like threads, and it uses some compiler support to make this efficient. And then Seta is the system I described earlier. So we've built 4 servers so far. I have over here on the right the lines of Flux code. Obviously, it's not the lines of C code, right, in these servers. This is just the new lines of Flux. And so one of the nice things is, live JPEG. Just downloaded live JPEG and plugged it in. PHP, God forbid you had to write that from scratch. So that's just shipped as a library, like many of these things are. So I'm going to show you just one benchmark here, which is a variant of SpecWeb 99, and then go over these various runtimes and the comparison. Yeah?
So did you have to write much new C code?
We had to write some new C code. It depended. I mean, you have to write some sort of glue for some of these things. Right? And so the amount of that varies. I believe that it's in the paper exactly how many lines, but I don't know what it is offhand. Okay. So here's the quick runtime graph. So we took a web server. We generated 3 different Flux versions, which are all blue. We have this one down here, which is the naive 1 thread per connection that, unsurprisingly, does not scale too well. And then we have this event-driven and thread pool system, which are way up over there. The thing at the very top, just above us, is Capriccio, which actually outperformed us here. I have a student who made a new runtime system, which is actually very cool. And we now are outperforming Capriccio. But, I mean, that wasn't really the goal. The goal was to match it. Right? The goal was to be able to take stuff off the shelf and come credibly within very high performance system. And then Seta is a sad story. Let me just leave it at that. That's how Seta performs. Okay? So we're doing 2x better than a paper that made it into SOSPI 01, so that's not too bad. Yeah?
Sorry, I keep going back to the runtime questions that
Yeah.
Manuel had, but just the focus question, if you're doing an event-driven style, it seems like the problem is that naively you would have sort of 1 event pump per processor, right? And then you respect the exclusion rules for the different systems.
Right.
There's always this problem, I wonder how you solved it, where if every processor could be in a particular component simultaneously because it has no concurrency constraint, but that component inconveniently makes a bunch of blocking calls, right, such that you don't perform other work.
Right.
How do you work around that? So you need to know in advance that it's going to put your thread to sleep, which is inconvenient.
Right.
And you want to shunt it off to a worker thread.
Yeah.
Do you inspect the component, or is this a declaration?
No,
or
they're
is
all
it
black boxes.
Uh-huh.
Basically, we have a shim, an extensive set of shims that shim all blocking calls and route them to helper threads.
So you shunt them just in time to some worker
That's right.
thread.
Exactly.
Okay, that's right.
Okay, so this is the discrete event simulator story. So we ran, this is actually the image server. I should have written that up here. So we ran the image server on a 16-way sun. But what we did is we disabled 15 of the processors. And we wanted to see, to go ahead and collect the data and then run the simulator to see how it would behave as we added processors. So we actually model in the discrete event simulator, the locks. Each lock has a queue. You model all of these things, the incoming threads, etc. But this is all generated automatically. The only thing that's missing are some observed parameters like arrival rate and so on. So what we did is we ran it on one CPU, and then we ran the simulator. So it's no real surprise. It comes pretty close, right? So then we went and we did it for all of the different numbers of CPUs with the powers of 2. So 2, 4, 8, 16. So we ran the code, and the parameters we used were only the parameters from the one processor run. So everything else is extrapolated from that run and using the Flux runtime, the Flux simulator, and you can see that the observed performance and the predicted performance are remarkably close. So the simulator faithfully captures the structure and concurrency control of the Flux program. And this happens for free, which is nice. Yeah?
One of Capricio's contributions was in order to scale to tons and tons of threads, they actually attacked the state consumption of the stack.
Yes.
Do you have an evaluation along resource consumption lines as opposed to sort of performance lines?
So one of the things about Capriccio that you're talking about, basically what they did is they used some compiler analysis to try to control the size of the thread stacks, right? So the default thread stack is, enormous, and you run out of thread stacks real fast, right? So the problem with Capriccio, and this is a roundabout way of getting to answer your question, is that there is no multiprocessor story at all. It only works on a single processor. And I hassled them about this, and they, it's coming soon, but this was a year and a half ago.
What you mean by
I mean their user-level thread scheduler only works on a uniprocessor, and they've never been able to actually adequately address the problem of multiple processors. So while I agree with the idea that shrinking these thread stacks is fine if you're going to go to a pure thread model, using thread pools or using some other runtime system, you get out of that situation. And the Capriccio story is, I think, half-baked at this point. So.
Okay, so is it fair to say then that Capriccio is trying to tackle the problem of sort of server capacity by reducing resource consumption for the threading model?
Yeah.
So my question was, well, how do you compare to that? And
Right.
It sounds like the answer is, well, Capriccio isn't really all the way there, so there's no comparison.
Yeah, it's hard to make we could make a quantitative comparison, but it's really unfair, right? The fact of the matter is that you could make a much cheaper system that just is single-threaded, that has no resource consumption, but that kind of sucks. So I figure Capriccio is still sort of apples and oranges.
Okay.
Yeah, but the problem remains. If you're going to use real threads, thread stacks are big. Okay, so let me talk very briefly about some future work. So who are these people? So the guy on the left is a grad student named Jacob Sorber. The guy in the middle is one of my colleagues, Mark Corner, also a professor at UMass. And the guy on the right is a zoologist. And the thing that's really important is what's in Mark's hands, which is this little turtle called a wood turtle. And so this picture here shows a wood turtle. That stuff on the shell is not natural. Those are passive radio transmitters. So here's the thing. The wood turtle is an endangered species in western Massachusetts. How do they know that it's an endangered species? The way they know is because the number 1 and number 2 predators of the wood turtle are cars and lawnmowers. And the number of dead turtle bodies has been dropping. Okay? But how many turtles are there? Where do they live? What do they do? Nobody really knows. Okay? So what they do is you get, the grad students of the zoologist out there with these big, like, walkie-talkie things with antennas. and they walk around in the swamp looking for turtles. All right? And then they ping one, and they find it, and they're real excited, and they run over and they find the turtle. Then they take the GPS out of their pocket, and they write down the reading then. So if you're lucky, you get one reading per day over a week per some small sample of turtles, which is a little bit unsatisfactory. So we're actually in the midst of deploying these little systems on the backs of the turtles. So they have to be very, very, very small. Massachusetts is very strict about these things. They've restricted us to 4 ounces. Now, I contend that this turtle is tough, and it could swim okay with a pound. But Massachusetts doesn't agree with me. So we're stuck with 4 ounces. So 4 ounces is really light. And the problem is we want to be able to get high fidelity information, high frequency. We want GPS. We want it all the time. But, if you've got a thing that's this big, what would be ideal is a car battery, right, to run the GPS for more than 2 days. But the car battery will clearly sink the turtle. So we can only really put in a tiny little lithium battery. And what that means is we need some way of harvesting energy from the environment. The good thing is these guys are cold-blooded. So they warm themselves by sunning themselves, which is perfect. So we have a little solar cell on top. So in this tiny little case, we have a solar cell, a GPS, a radio transmitter. So if you get near another turtle, you can broadcast information about where you've been and share. And then if one of those turtles happens to get near one of these master stations that we've set up on lampposts, then they can upload their information to the 20 gig hard drive that's there. Okay? The problem is, from a programming standpoint, this is complex because you can't just say, oh, run GPS all the time. If you run GPS all the time, the battery is drained in an hour. And we'd like the thing to run forever, at least for the lifespan of the turtle, let's say. Okay? Which is maybe not forever with all the lawnmowers. But anyway, so we have this problem that the power is going up and down. So we've extended Flux, and it's a terrible name, I admit, but we call it eFlux, okay? And the insight here is that client-server is actually remarkably like sensors. What do sensors do? There's events coming in from the environment, and they respond to them. And the events are asynchronous and can happen at the same time. And guess what? That's more or less what servers do, right? So we found that it's a good match, at least conceptually, but we needed to address this problem of power states. So what we've done, we actually have a way for the programmer to specify a bunch of power states in a lattice, and then you can decorate these flows with these power states. And so if you're in flow and it says power state high, it won't run if you're in power state low. So it's sort of another argument that controls dispatch. And then we've built a very sophisticated runtime model that actually incorporates days of sunlight data in western Massachusetts for different times of the year. It is actually pretty sunny, turns out. But it tries to predict how much sun is coming. If I'm in this low power state and I haven't uploaded in a while, maybe I do want to go and do the GPS thing or turn on the radio transmitter and so on, because odds are good that sun is coming, right? So there's all sorts of these things we can do, and we dynamically adapt and so on. So the cool thing is that we can push all of that information into the runtime, and then the programmer who actually is doing the program logic just doesn't have to think about it at all. This has so far turned out to be a real win. The programmers before who were working on this, these grad students, were using this thing called Nessie, and they were completely stymied. It was just too difficult to reason about. All right, good. So there's the conclusion of Flux. Right, so you can use sequential C code. You can build these servers. Maybe you can build turtles. And you get predictable performance, etc. Right, so that's it for performance. So if you're not interested in anything but performance, you can leave now. The next part of the talk is not about performance. Yes, Manuel.
So this is nice, but I think you kind of set us up at the beginning, right? You said, well, one of the problems is we have cores and we don't know what to do with it, right? Which means that problem is finding parallelism. And then you showed us this embarrassingly parallel problem, right? Where that's not the problem. The problem is it's kind of controlling parallelism and not having too much of it. So
right.
Do you have a story for the other problem too?
The magic story where I extract parallelism from spec applications?
Because I mean, it's well known that the servers are embarrassingly parallel, and this is like the most studied infrastructure and architecture that people who are building servers, they know exactly to build them this way, right?
So yes and no. So I would argue that it still remains a matter of controversy as to what the best runtime system is and how to build these servers. And it remains complex and difficult to build these servers. Okay? People spend a lot of time. They don't know how the server is going to behave. I myself have personally consulted for people trying to address their server performance behavior characteristics. Right. So that said, I'm going to say something controversial. I know, Sting, I'm sorry. I've never done this before. I have not yet been told what the great application class is for which we need multicores. Because that's not how it worked. We don't have multicores because of the crying application need for multicores. We have multicores because the architecture community ran out of ideas. Okay? So I don't know of any application for which we really need to extract all this parallelism. Does Word need all this parallelism? Maybe. God forbid. Right? But that said, I think that there's one application class that we know very well does need parallelism, and it's servers. And it still has been difficult to program these servers and reason about them and produce correct servers. In fact, I know, I'm going to finish here because I'm going to run out of time for the rest of the talk, but I know of a major commercial server serving millions of people that recently deadlocked. Right? That sucks. And it is just testament that people really have not solved this problem, which of course is motivation for the whole atomicity and transactional memory line of research.
But I mean, your approach to correctness is of course also half-baked in the sense that, if I specify my logs incorrectly, it's going to be just as bad as before, right?
Yeah, so actually,
It's higher level, and I agree, it's nice, but I think it's only a really small step in the right direction.
So, well, we can quibble about the size of the step. But I actually am working with Mike Hicks on using static analysis to look inside these pieces of C code to verify the correctness of these things. Okay. So, well, I have 8 minutes. Is that right? This will be a blast.
You have till 12.
I have till 12. Oh, okay. All right. Okay, that's fine. All right. So if you've already seen this, I know a couple of you have. All right. So this is joint work with Ben. This stems from work I did when I was here last summer. So what does this address? This addresses the problem of memory safety. So you've got these C and C++ programs, and they have problems. Right? Some of you may have heard that they're memory unsafe. This is a small list of some of these memory problems. So you can have a double free. You can have an invalid free where you free the wrong thing. You can do an uninitialized read, buffer overflows, and dangling pointer errors. So this talk is actually just about the heap. It's about memory errors that occur in the heap. I'm not going to be talking about the stack at all. All right. So how do we deal with this? So there's several ways of dealing with this problem. The first is the most popular way, which is to do nothing at all. Right? So this is the approach taken by Windows and the C library from GNU and so on. Your program may run, may do something crazy, it may crash. It's unclear. There is this piece of work called RX, which is out of YY Joe's group in Illinois. And this one, the idea is I run the program. If it crashes, then I roll back to a previous state, and I do something like pad out memory allocations and so on, and hope that it continues to go on. What this doesn't do, and it's fine, what it doesn't do is, first, it only detects crashes. You could be off doing God knows what, and that's not going to show up as an error. And second, it's not really guaranteed to fix the problem. But it has been shown to work for some cases. So another system, which is also unsound, but will absolutely, definitely continue, is called failure oblivious computing. This is from Martin Reinhardt's group. So how many of you have not heard of this? Okay. Well, at least 3. Good. All right. So here's the idea. I have a compiler which detects all out of bounds and other invalid operations. when you detect such an operation, like an invalid read, I read from nowhere, then in the first incarnation of this work, you make up a value. Okay? In fact, Martin proposes a whole sequence of values, and then the values should loop, because that will ensure termination and things like this. And then if it does something bad again, then you again fabricate a new value. And if you write into an illegal area, either you drop it or you cache it so that maybe you read it again next time. Okay? But it will definitely continue. What it's doing is unclear, but it will definitely continue to run. Okay? So another alternative, which I think is more popular, at least it increases the comfort level, is a fail-safe approach. As soon as something bad happens, you fall on your sword. You say, oh, God, I'm about to overflow something, and then that's it. Game over. Right? So this suffers from a few disadvantages. So the first is, first this is a C-only solution, and it requires your C source, all of your source, and it instruments it. And the slowdowns can be substantial. So you can get from 30% to 20x slowdowns, which is a lot. So it also stops as soon as you have any error at all. And some errors could be benign. Let me give you an example of benign error. I allocate 16 bytes for every 12-byte object. Then I write the 13th byte, which is benign, right? Because that is not going to be used by any other object. But any of these compilers will immediately complain and halt.
But that's
right?
easy to fix, right? If they knew the memory allocation.
If they knew the memory allocation layout, they could certainly check for it, and that would be okay. But other errors could also be benign. That's not really the main issue. The main issue is that 20x slowdown makes it useless for deployment. Yes?
Isn't there another approach, I thought, in another group here in MS Research, where they're instrumenting the binary instead, and they were able to achieve more reasonable performance?
I'm not aware of it.
I remember the names offhand. So.
Okay. I'd be interested to hear. Okay. So what I'm going to talk about now is this tool called DieHard. So DieHard is going to provide something that we call probabilistic memory safety. So what this will give you is not 100% sound, but also not 0% sound. It'll be somewhere in between. The idea is you're going to run correctly in the face of errors with high probability. And I'll actually be able to say what that probability is. And it relies on two things. First, it relies on a fully randomized memory manager. And I'll explain how that works. And this is going to increase the odds of benign memory errors, and it's also going to ensure that every user is going to see a different heap layout, which will turn out to be important. In particular, the other thing you can do is you can go ahead and replicate the process. You can take process X and have 3 copies of it. All right? And we're going to run these replicas simultaneously and vote on the results. And this has numerous benefits, which I'll explain both analytically and empirically. But at a high level, it can detect all kinds of errors. It can detect errors that cause crashes, and it can detect errors that just go off and do crazy things, right? Because they won't agree. So what this does is it gives you a trade-off. You give me more space and more cores, and I'll give you more reliability. So let me explain briefly how we're going to ascribe some semantics to these programs that are broken so we can reason about them. So normally in the PL community, if you have a memory error, you consider the program to have no meaning. It has this symbol which means bottom, right? It has absolutely no meaning at all. But if we consider the case where we have an allocator that presents the view of an infinite heap, a heap that is literally infinitely large to the program, then you can make some erroneous programs completely sound. So think about it. If you have an infinite heap, all news can be fresh. That is, as soon as you need more memory, you just go get more because you have an infinite amount of memory, right? And you don't care about delete because why? Delete is just to reuse memory, and I've got so much. I don't need to delete any, right? So this immediately gets rid of a large class of errors. In addition, the heap is infinitely large. Why not make every object infinitely large too, right? Why not? So if every object is infinitely large, then it's impossible to have a buffer overflow. You can't overwrite some other live object and so on, right? So the cool thing about this is that for correct programs, basically this is transparent. A correct program cannot portably detect whether it's running on an infinite heap or not, right? It could go ahead and count, all right, I've allocated 100 objects and But that's no proof of anything. You could just be in a larger memory space, right? The cool thing, though, is that you have programs that used to have no meaning at all, and now they're sound. So what we're going to do is we're going to actually approximate these infinite heaps, but what we call M heaps. And this is going to provide probabilistic soundness. So M here is the factor of increase over the maximum amount of memory required. So if your program needed 100 bytes and M is 2, then it'll consume 200 bytes. So here are a couple ways you could imagine doing this. You could pad all the memory allocations, right? I ask for 8, I'll give it 16. And I could defer deallocations, right? Which is like I'm going to wait until 2 times as many objects have been freed. So this would be reasonable. It's simple, but it doesn't provide any protection at all for larger overflows. So if you have an overflow of size 9 and your pad was of size 8, then you have 0 soundness, right? In addition, it's deterministic. If you just say I'm padding every object by this much and I'm deferring by this much, if I have a bug that crashes one of those things, it's going to crash everybody, right? So that's not desirable. So we propose to randomize the heap. That is, we're going to take the heap and we're going to randomly lay out all the objects within the heap. And this is going to provide probabilistic protection against errors, and it's going to be independent across heaps, which means that this replica thing will actually work. And it also means that multiple users will potentially be able to avoid these bugs. Can hit one and it won't hit everybody else. Now, there is a big question mark here, though. How on earth can we randomize the heap efficiently? So you have a question.
Just for completeness, do infinite heaps have anything to do with another class of memory error that you didn't mention, which is that a program might sort of fabricate a heap pointer? Is that just sort of not addressable, or is there some interaction that you didn't mention?
You mean we forge a pointer and then we go and write to it, say, or read from it?
I mean, one class of error is you're doing pointer arithmetic and you screw it up, so you effectively have a fabricated address.
Yeah, that's right. So the analysis is actually done assuming that that's the model that you use for buffer overflows, that you fabricate a pointer somewhere into the heap and write. So, yes.
But it's relative to some object, I think.
Oh, okay, that's the question. Right, so yeah, no, I mean...
It seems like the padding model is that, I might sort of overshoot an allocated object.
Yep.
That's sort of distinct from just making up an
That's
address,
right.
which isn't relatable to any object.
That's right. So we're going to get to this in the analysis section. But in fact, that's exactly what we do, is we just assume you have a random pointer somewhere in the heap that does something. And then what is the probability of avoiding that kind of error? Okay. All right. So, so we first went to try to randomize the heap. Said, okay, let's start with the normal heap. It's a free list-based heap. Well, how do you randomize a list? Well, okay, it's clear to see how you could randomize a list, but then how do you do it efficiently? That's not clear. More importantly, these free list-based heaps are really susceptible to small errors, right? So the free list-based heaps typically have an object, and they have a little header that's before the object. Well, if you have a 1 byte write into that header, game over, right? It's corrupted. How do you deal with a double free? Right? Well, you can check some magic cookie potentially to see if the object is freed. That could be corrupted. You could scan through the whole list to try to find the object. That would not be smart, right? So double frees are a bit of a problem. So we then said, well, what else could we do? And Wilson in 1990 had proposed this idea of using bitmaps for memory allocators. Which is fine, but if you're randomly allocating objects in a space using bitmaps, you can end up with catastrophic fragmentation. So let me show you what I mean. These big boxes are pages, and now I'm going to randomly allocate these objects. Right? Now I want to allocate a page. Well, I'm hosed. Right? There's no place for me to slide that page into. And moreover, it's not really that efficient to go search through a gigantic bitmap to find an empty space. Wilson proposed a few things, but they're all tricks like, read 32 bits at a time. But, okay, that's, it's fine. But if you have, millions of bits, it's not really helping that much. Okay. You could build, that's right. So, yeah, that's right. So you could build a hierarchy of bitmaps. You then actually have an issue of overlap across the bitmaps. So if you say, so I'm not going to go into this slide. If you have this space and this space, well, you really want to be able to put an object in the middle as well, right? So it's not that simple. It's doable. I think it's doable. Yeah, it's definitely doable. It's not. That's not really the issue here, though. The issue really is randomization, right? So if I want to randomly allocate objects in this bitmap heap, I'm going to end up with fragmentation. So what we do to solve this is we segregate all these sizes of objects into their own distinct region of the heap. So I should add, the implemented version of DieHard that you can actually get now is a more sophisticated heap structure, but this is simple to understand. So conceptually, all we do is we carve the heap up into chunks, and then each chunk is devoted to a different size of object. And here they're powers of 2. So for instance, these green things indicate allocated objects, and the ones in the bitmap mean that they're allocated, and the 0 means that they're free. And so here, this is an object of size, say, 8. These are objects of size 16, and so on. So the key thing to realize here is, first, a bit doesn't represent a word or a smaller chunk anymore. It represents an entire object, right? So we don't have to find the right space to fit. If we go to the right partition, we can immediately find the fit. Moreover, you can't get any sort of fragmentation. If there's space available that for a size 8 object in the size 8 heap, there's space available, right? It can't be broken up. So this is crucial. So now, how are we going to do allocation in free? So allocation turns out to be pretty quick. We're going to compute the size class of the requested object. We can do with a quick log operation. And then we're going to randomly probe the bitmap for a free. And it turns out that this actually is very much like a form of hashing. And the expected number of probes, if m is 2, that is, you always have over-provisioning by a factor of 2, the expected number of probes is bounded by above by 2. So it's fast. All right? So we go, we say I have an object of size 8. I'm going to allocate from here. I randomly flip an object. Good. That one was not free. I claim it. Okay? And so that's going to be quick. So what about free? Free is very straightforward. It's basically arithmetic. You find out which pointer, which part of the heap you're in. And then we can add some validity checking. Did you really mean to free this object? Right? Did you try to free this pointer instead of this? So we can check to see if you've aligned it to the right address. That's just quick pointer math. If you double free, it has no effect. Setting a bit to 1 1,000 times, still 1. And then or to 0, I mean, in this case, you just reset the bits. So this has this benefit of avoiding these 2 errors. So here's an object we're going to free, and we flip the bit. Very simple. All right. Great. So now here is a heap after some number of objects have been allocated. So the numbers here just denote the nth object allocated in that partition. So the first one, second one, third one, fourth one, fifth one, etc. So every time I run the program, I'll have a different heap. So the errors across the heaps will now be independent. So what this means is you'll get, this is, say, somebody else's heap, and same program running, and the heap layout is totally different. So pretend we're running, I guess I should change this to IE for this audience. But pretend we're running Mozilla. Mozilla has an overflow, which happens. And it overflows from object 2, let's say. Well, that's going to stomp on object 4 in the heap on top. But in your Mozilla, it might be that it just lands in some empty space. And the odds of it landing in empty space, intuitively, are basically 50-50. Right? If I randomly choose and the heap is completely full, and I just pick some random place to land, I'm going to land on an empty space with a 50% chance. Okay? If the heap is twice exactly. All right? And I'll go through all of this stuff. So this is great. Fewer people's Mozillas will crash, let's say. Well, great for Mozilla. Again, should have changed it to IE. But maybe I don't care about other people. Maybe I'm a selfish bastard. And I want my Mozilla not to crash, right? The other people's can crash, but mine better not crash. So here's what we can do. So what we actually do is we have this approach where we replicate the process, the whole process. And then all input gets broadcast to different replicas. So here we have 3 replicas. Each replica has a different random seed, which means its heap is going to be differently randomized. Then, when we go to output, all of these guys send their results, whatever the output is. Let's say this is a standard in, standard out program. So it reads a chunk of memory, gets replicated to everybody. They go and they execute. Then they go to write something to standard out. They fill the standard out buffers, and then the buffers are compared. And you vote. That is, you try to see if anybody doesn't agree. And if a replica doesn't agree, you say that replica had an error. Now, the assumption is if replicas do agree, because the errors are independent, and the odds of having an identical heap layout are vanishingly small, you assume that consensus equals correctness. Yes? So there's a barrier synchronization on the output.
And the output
And
in
on
this
the
case
input.
is heap writes?
I'm sorry?
The output in this case is heap writes?
No. God, yeah. No, no. This is like standard out.
Okay.
Yeah, yeah. If we were to, I mean, you could imagine capturing things at a fine grain like that. Certainly, you'd get an enormous slowdown.
So are you assuming these programs don't use the disk, for example?
That they don't use the?
The disk.
The disk. I do assume they use the disk. But, so here's the deal. The initial prototype of this that was described in the paper only intercepted standard in, standard out, and a few other things, notably time of day, because web servers, for instance, write logs. And if you're going to be intercepting file I.O., and everybody has a different time, you're going to have a problem. So what we want to be able to do is to have the nth call of time return the same result across all the replicas. The same is going to be true for file I.O. and for sockets and all of those things. If you get a socket read, then, and it comes off of whatever this particular socket ID is, has to be the same for everybody. When you write, you have to buffer everybody's writes, and then you send it out to the socket, just one of them, the one that passes.
If it's, again, using the web browser example, doing say cryptography or something that depends on a random number, that would be an issue as well.
Yeah, so basically, so you can have non-determinism in your application as long as it doesn't bleed to output, right? So that's actually an excellent point about crypto. But yeah, so that's the deal. Right now, this particular infrastructure only handles non-deterministic output streams. But I think crypto, I mean, if the random number is not generated on a if it's not generated afresh by every replica, if it's something that's stored, but it's cryptographic, then I think it's okay. Okay, so let's go through some results. So I'm going to show you some analytical results. I'm going to give you a flavor with pictures of how this works, and then show you the math. I'm actually going to show you the case where the protection that DieHard offers is the lowest, which is for buffer overflows. The reason for this is we modeled buffer overflows very aggressively as these random writes that I described earlier. I'm not going to talk about uninitialized reads or dangling pointer errors, for which the protection is the best, but you can look in the paper for that. And then talk about some empirical results, notably runtime overhead, and then how it actually works in the face of errors. So here's the analytical results. So suppose we have a buffer overflow. The overflow here is I randomly choose some object to smash. That's my model. Not really a typical overflow, but it's the most conservative one for the analysis. So if the heap is half full, right, you have a 50-50 chance of avoiding the overflow, right, and 50-50 chance of having the overflow land on something allocated. So here we're happy because the random write just stomped on some freed data, and so we don't care. But here we're sad, couldn't find a smiley face, sad face. We're sad because it landed on live data, and we consider that to be a failure, even if the live data is never reused. All right? So what about another overflow? Right? So we have only a quarter chance of surviving 2 overflows, and only an 1/8 chance of surviving more overflows. So the probability of avoiding an overflow, that is, in the face of these overflow repetitions, the probability of having no impact of this overflow is at least 1/2 to the n, which is not that great. Right? It's better than 0, but it's not that great. Okay? But the replicas help a lot. So here, let's say that all we care about is avoiding a crash. To get correctness, you actually need at least 2 replicas. But if you want just the program to keep running, let's say we just have 1 replica. This is simpler for this description. So what we're going to do is we're going to say, well, we have a 50-50 chance of landing in bad, in bad, and in bad. But the probability of an overflow in every single replica is actually low. It's an 1/8. So the chance of avoiding an overflow in 1 replica, at least 1, is 7/8, which is pretty good. So the replicas really buy you a lot. So this is the formula up top where F is the amount of free space and H is the amount of heap size. So if you have said, the maximum fullness is a 1/2, you obviously could go up and you could go down. So your heap could be less full or could be more full, no more than a 1/2 full. N is the number of overflows, and K is the number of replicas. And so this graph depicts the probability of avoiding an overflow of 1 object. The purple bar is when the heap is an 1/8 full. Maybe I should have said purple for this one. The reddish bar is a quarter, and then the green bar or yellow bar is a half full. And so you can see that the probability is pretty high with one replica for, when it's an eighth full, only 50% as described earlier. But as you add replicas, 3, 4, 5, 6, the odds get higher and higher that you're going to avoid these errors. Yeah?
I think you mentioned this, but you want to be able to detect the replica that didn't have the failure. So I think you mentioned that.
I just mentioned for this analysis, we're going to assume crash failure. That's right.
So you can sense which replica succeeded by knowing it.
Yeah, it's a weak version of success, right? Success means it keeps running. If you really want to be stronger, you have to say at least 2. But at least 2 actually works okay, too. You get the same sort of geometrically increasing odds of avoiding overflow as you add replicas. But it's simpler to think of at least 1 than at least 2. So. Okay, so what about runtime? So, this randomized allocator, you would think would be expensive because it's, randomly allocating, for Christ's sake, right? So I ran it, this is just, no replication, just the randomized heap, against some well-known, hilariously allocation-intensive programs. These are widely used in the memory management community as kind of stress tests. I mean, some of these things spend, like RoboOp, I believe spends 40% of its time allocating and freeing objects. All right, that's all it does. I think that it allocates and frees over its lifetime 1.5 billion objects, but its peak footprint is like 20K, okay, to give you a sense. So we ran this against Windows, and you can see, malloc is the black bar, so it's normalized to malloc. And, in some cases, it actually does better, and surprisingly, significantly better. And on average, it's pretty close. Yeah?
But the problem in the randomized allocator is not the allocation time, it's the usage time, because you're spreading your load on a much wider variety of pages, so you lose locality.
This is not allocation time. That's right. That's a good question. I should have stressed. On this y-axis, this is normalized total execution time. This is not allocation time.
But,
okay?
For example, that would explain why RoboOp would actually perform a lot better, because its footprint is so small that none of this locality really matters.
That's unclear. That's unclear. I mean, if you think about a free list allocator that uses, say, a stack-like discipline, right? I allocate a bunch of objects, and I free them all. I allocate them, I free them. I'm reusing the same memory over and over again. That is definitely not happening in a randomized allocator, right? You have no chance at all that you're reusing the same objects iteration after iteration. And in fact, in this particular case, they're spread over, if I recall correctly, 32 megabytes of space. And you'll see that this is partly a function of the Windows allocator, as I'll show on the next slide. So this is runtime on Linux. These are the same applications. And you can see the black bar here is the GNU libc allocator. And then the blue is the Bohm-Weiser collector. This is just to show that we're sort of close to conservative garbage collectors in overhead. But the green bar here is DieHard. So this is a lot different, right? Before it was almost the same, and here it's like 1.4. So I speculate that the reason for this is locality. I know that the reason for the giant bar on the right is locality. It's TLB. Okay? Now, these are all results for the initial version of DieHard, which had one giant heap. Okay? The new version of DieHard, that's the 1.0 version, is adaptive, and it grows to fit. So you would never get into a situation like you have with T-Wolf over here. On the other hand, even including these outliers, the geometric mean, this is like 10%. 10% with randomized allocation. Right? So, locality, schmocality. Right? This is application performance. So it's kind of unclear that locality, at least at the L1 and L2 level, make that much of a difference. And remember, this is I tuned the hell out of the allocator, but it's still making random numbers, right? Every allocation is still several multiplies and mathematical operations and so on. So, all right. I will say I've run this under Valgrind, which measures, you can run it and get cache values out. And yeah, the locality is a disaster, but its actual impact on runtime is surprisingly small. Caches are big enough, I guess, is the take-home message for many applications. Clearly, it's not true for every application. Yeah. Yeah. Okay. Right. So
does this mean that locality really doesn't matter?
Let me put it this way. It means two things. So first, if your object size is close to your L1 size, then jamming objects together doesn't matter, right? I mean, ideally, the best situation for caching is you get object level caching. I use this object, and there's the object, right? You'd like prefetching and other things to happen. But this totally undermines prefetching, right? You could have been allocating in a linear fashion with the Linux allocator, and you're definitely not doing that now. No prefetcher is going to figure this out. So you tell me. I mean, clearly, your mileage may vary. But I would certainly say that spec doesn't make much of a difference. Okay. So fine, runtime. That was I promised I wasn't going to say anything about performance, but I guess I did. I would say that it's a credible story. You end up with a geometric mean of about 10% penalty, right? You automatically get double free protection and invalid free protection by the nature of the allocator. So what about other kinds of errors? So in addition to these other kinds of errors that we naturally get for free, we want to be able to show that we can protect against dangling pointers and overflows. Right? That's the whole point. So what we did is we wrote a little error injector that could take a running program and inject certain faults. So overflows are easy. You ask for 8, I'll give you 4. Right? Bing, overflow. Dangling pointers are more complicated. You have to run the program once. You get the list of all the allocated objects, and then you free objects a little bit too soon. So for the dangling pointer case, 50% of the objects we freed 10 mallocs too soon, which is, I mean, freshman computer science programmers don't do this bad, right? Maybe 40%. Okay? So if you run it with glibc, it crashes every single time. If you run it with DieHard, this is for the espresso benchmark, by the way, 9 out of 10 run correctly. With overflows, unsurprisingly, if you overflow every object, if you underallocate every object, things die fast. So we did it at a 1% frequency, and every object was underallocated 1% of the time by 4 bytes. So glibc crashed 9 out of 10 times, and then there was an infinite loop on the 10th execution where infinite means ran longer than 5 minutes. And DieHard, it ran 10 out of 10 times correctly. That is, the output was identical to the correct run. So we also measured it on real faults. So there are 2 applications, 2 real apps that we used. One is this web cache, a popular web cache called Squid. And it had an overflow that crashed BDW and glibc, ran it 10 times, no apparent effect. And with Mozilla, there was a dangling pointer error. And like I said before, dangling pointer protection is actually really, really high. So it causes a denial of service attack in glibc and Windows. You go to a particular web page, the browser freezes. But if you run it with DieHard, nothing happens. Yes?
So is this one copy of the process?
This is one copy.
Some amount of over-provisioning?
This is one copy, 2x.
Okay. So
yeah.
Presumably things could be even better with replicas.
That's right. In principle, so certainly you could withstand more overflows. The dangling pointer protection is so good. Replicas do add something, but you're already at 90-some%. The intuition here is you've got a big heap. I free an object too soon. Now I need to overwrite it. Well, random, right? When am I going to hit that object? Right? So if the heap is large relative to the number of objects, if the heap is large and I'm allocating randomly, it's highly unlikely I'm going to hit that object soon. Okay. So conclusion. Here are those cores again. So randomization and replicas gives you probabilistic memory safety. In fact, replicas are not necessary. You can use, you can just use this as a plug-in replacement for your memory allocator. Clearly, it provides more protection than you have today, which is 0%. And I think it's a useful point between absolute soundness, where the program stops, and unsoundness. And the take-home here is, look, we have this hardware. Let's use it. And this is what ECC does. This is what RAID does. And you trade hardware for reliability. And takes advantage of these hardware trends. Certainly multi-core CPUs and memories are getting larger. If you have a small to medium-sized footprint application, then replication is fine. For a very large footprint application, just pushing the limits, you don't want to use DieHard. Okay, that's the end. You can go to my webpage, of course, has these links as well. But you can download DieHard. There's a Linux and Solaris version that's standalone and replicated. The Windows version is standalone only, unless somebody can explain to me how to do fork in Windows. And then Flux. If you go to flux.cs at UMass, it's actually a web server written in Flux, and you can do the BitTorrent, and it's the Flux BitTorrent. So that's kind of cute. And that's it. Thanks for your attention.